Welcome to AI News Digest 2026-06-12. Today's 10 stories. Story 1, When AI Builds Itself Anthropic. Story 2, From AGI to ASI. Story 3, Did You Lie? Evaluating lie detectors across model scale and belief-verified model organisms. Story 4, Benchmarking AI agents for addressing scientific challenges across scales. Story 5, General-purpose large language models outperform specialized models, Nature. Story 6, Strategic Decision Support for AI Agents. Story 7, Arbor, Tree Search as a Cognition Layer for Autonomous Agents. Story 8, Evaluation of Large Language Models in Infectious Disease Decision-Making. Story 9, Deployment-Centered Evaluation, Predicting Query-Level Rejection Risk in a Clinical LLM System. Story 10, Rethinking Psychometric Evaluation of LLMs, When and Why Self-Reports Predict Behavior. Story 1, When AI Builds Itself Anthropic. Here's a story that sits at the crossroads of psychology and artificial intelligence, and it has real consequences for how safely we deploy the powerful language models that are increasingly shaping our world. A team of researchers from Caltech, Cambridge, and collaborating institutions just published a paper asking a deceptively simple question. When you ask a large language model to report on its own behavioral tendencies, does what it says actually predict what it does? And the answer turns out to be nuanced in ways that matter enormously for AI safety. The background here is important. Previous research had documented what's called self-report to behavior dissociation in language models. Essentially, models seem to say one thing and do another. This was taken as evidence that psychometric self-assessments of LLMs are basically useless for predicting behavior. But this new paper argues that conclusion was premature, because those earlier studies used the wrong psychometric tools. Specifically, they relied on the Big Five personality framework, traits like openness, conscientiousness, and neuroticism, which is notoriously weak at predicting specific behaviors even in humans. So finding that Big Five self-reports don't predict LLM behavior doesn't tell you much. The researchers instead applied the theory of planned behavior, a framework that measures intentions targeted to specific actions rather than broad personality traits. Running experiments across 11 frontier language models and 4 behavioral tasks, they found something striking. Within a shared conversation, theory of planned behavior self-reports achieve human-level coherence with actual behavior. The Big Five does not come close. But there's a critical catch that should concern anyone deploying these systems. When the researchers tested what happens with persona prompting, giving a model a stable character identity, which is a very common practice, they found that self-reports became more consistent, but actual behavior did not align. In other words, the model looks more predictable on paper, but isn't actually more consistent in practice. That's a dangerous gap. And for highly context-sensitive behaviors like sycophancy, coherence essentially collapses across separate conversations, regardless of the psychometric instrument used. The takeaway for the field is clear. Coarse personality frameworks need to be retired from deployment evaluation, replaced with task-specific instruments, and even those must be validated carefully across contexts. This isn't just academic, it's a direct challenge to how AI safety is currently assessed. Story 2, From AGI to ASI. A new peer-reviewed study published in the journal Infection and Drug Resistance on June 12, 2026, offers one of the most rigorous head-to-head comparisons yet between large language models and specialist physicians in a specific medical domain. Researchers from Zhejiang University's second affiliated hospital tested 4 frontier AI models, DeepSeek R1, ChatGPT-5, Grok 3, and Gemini 2.5 Flash, against infectious disease residents using both standardized examination questions and real-world clinical cases. The headline finding: on examination-based assessments, the AI models performed comparably to the resident physicians, with no statistically significant difference in accuracy or score rates. That said, the results were nuanced. The AI models showed a trend towards stronger performance on low-order, knowledge-based questions, the kind that test whether you've memorized a textbook. Physicians, on the other hand, tended to do better on case-based questions requiring higher-order clinical reasoning, though again, these differences didn't reach statistical significance. When the researchers moved to real-world clinical cases, a set of 10 patient scenarios reviewed by expert clinicians. The LLMs scored highly across multiple dimensions: accuracy, completeness, individualization, safety, and readability. All four models performed comparably to each other, which is itself a notable finding suggesting that frontier AI models have largely converged in their infectious disease knowledge base. Perhaps the most practically important result was this: when doctors made clinical decisions with AI support, their accuracy showed a trend toward improvement compared to decisions made independently. The effect didn't reach statistical significance, but the direction is consistent with a broader pattern in the medical AI literature showing that human AI teams often outperform either alone. There are important caveats here. The clinical case evaluation involved only 10 cases, which is too small to draw strong conclusions. The study was done at a single Chinese academic medical center, and the comparison group was residents, not attending physicians. Nevertheless, the study provides a useful framework combining exam questions with real clinical cases and measuring human-AI collaboration that larger future studies can build on. For healthcare systems weighing whether to integrate AI tools into infectious disease workflows, this paper offers cautious but genuine encouragement. Story 3, Did You Lie? Evaluating lie detectors across model scale and belief-verified model organisms. Researchers from Stanford and collaborating institutions have published a paper that tackles a problem at the heart of real-world clinical AI deployment. How do you know, before an AI system generates a response, whether that response is going to be useful or rejected by the clinician who asked the question? The paper, submitted to arXiv on June 10, 2026, describes a deployment-centered evaluation framework built around an LLM system embedded directly in the electronic health records of an academic medical center. The central innovation is a pre-response classifier, a model that takes in information about a clinical query and its context, and predicts the probability that the user will reject the AI's answer before the answer is even generated. Over 4.5 months of prospective real-world deployment, this classifier achieved an AUROC of 0.719, meaning it can meaningfully distinguish between queries likely to produce useful responses and those likely to fail. What makes this work particularly interesting is what the researchers found improves prediction accuracy. It's not just the content of the query, it's the deployment context, who is asking, which department they work in, and which language model is being used. A question from an emergency physician carries different failure risk than the same question from an infectious disease specialist. That contextual sensitivity is invisible to traditional benchmarks, which evaluate AI on curated test sets without any information about who is actually using the system or how. The researchers argue, convincingly, that static benchmarks are fundamentally misaligned with clinical reality. They measure factual correctness, require densely annotated datasets, and average performance across all queries equally. But in a live hospital environment, what matters is whether the clinician found the response useful enough to act on. Rejection is a direct, if sparse, signal of failure. The practical payoff comes from two downstream applications: guardrail triggering and abstention. If a system can predict that a response is likely to be rejected, it can either route the query differently, ask for clarification, or simply decline to answer, all before a potentially unhelpful or misleading response reaches a clinician. The AUROC of 0.719 is a solid starting point, and the framework opens the door to context-aware safety systems that could meaningfully improve the reliability of AI in clinical settings. Story 4, Benchmarking AI Agents for Addressing Scientific Challenges Across Scales. A large collaborative benchmark paper evaluating AI agents on real scientific research tasks, addressing gaps in existing benchmarks that reduce science to static problems. The benchmark captures complexity, heterogeneity, and extended reasoning required by actual scientific work, with support for interactive evaluation. Authors include researchers from Yale, Stanford, Harvard, and other leading institutions. Story 5, General-Purpose Large Language Models Outperform Specialized Models, Nature. A Nature-published study evaluating frontier LLMs, including GPT-5.2 and Gemini 3.1 Pro preview on specialized tasks, finding that general-purpose models outperform domain-specific ones. The study used 1,000 evaluation items accessed via API in early 2026. This provides important empirical benchmark results relevant to LLM deployment decisions. Story 6. Strategic Decision Support for AI Agents. This paper examines the shift in agentic AI systems, where AI agents act on behalf of users while humans become support mechanisms, inverting the traditional human-AI decision support relationship. It addresses reliability and alignment concerns arising from this role reversal, where agentic errors can be consequential, relevant to both practical deployment and safety alignment research. Story 7. Arbor. Tree search as a cognition layer for autonomous agents. Arbor introduces a multi-agent framework using structured tree search as a cognition layer, maintaining an explicit search tree of scored hypotheses as shared working memory across agents. Unlike prior autonomous optimization systems that operate on isolated stateless targets, Arbor treats failures as diagnostic signals in a stateful action space. This represents a concrete architectural advance for agentic AI systems. Story 8. Evaluation of large language models in infectious disease decision-making. A peer-reviewed evaluation of multiple frontier LLMs, including DeepSeek R1, ChatGPT-5, Grok 3, and Gemini 2.5 Flash, on infectious disease clinical decision-making tasks. The study demonstrates strong capabilities across models developed in different global contexts. This is a practical benchmarking study with direct clinical application relevance. Story 9. Deployment-centered evaluation, predicting query-level rejection risk in a clinical LLM system. This paper critiques static benchmarks for clinical LLM evaluation and introduces a deployment-centered approach focused on predicting query-level rejection risk in real clinical systems. It addresses blind spots in standard benchmarks, including their focus on correctness over user acceptance and reliance on dense annotations. Authors include researchers from Stanford, Sanmi Kaijo, Nigam Shah. Story 10. Rethinking Psychometric Evaluation of LLMs. When and why self-reports predict behavior. This paper investigates when psychometric self-reports from LLMs reliably predict their actual behavior, a key question for safe deployment. It improves on prior work by using more behavior-specific traits beyond Big Five personality and better context matching. The findings have direct implications for using low-cost probes to anticipate LLM behavioral tendencies before deployment.